This is an example of how to acquire data for force reconstruction, for data that has to go into the Mendeleev-Meyer force project for the construction of feature libraries. The first thing we'll do is to mount the cantilever. As we can see here, the cantilever is already mounted. It's an AC240 cantilever, standard, and we're using an Asylum Research cipher, also an standard equipment in AFM, in the AFM community. So what we can see now is the cantilever is quite blurry. First thing to do is to find it. So I'll click down. The image is getting more blurry, so I'll go up. So now I find the cantilever, and I put the spot of the laser just in the middle of the cantilever, and I tell the system that this is the tip, so I set. Next thing to do is to tell the optical microscope the relative position of the cantilever relative to the surface. So the first thing we need to do is find the surface. That's what I'll do by clicking down. We will know that we found the surface when we get a clear contrast from a circle, white circle on the surface, and a white region everywhere else. We see that this is the clear sharp edge. So now we'll do 3 clicks, 1, 2, 3. This is to make sure that we don't crash the tip onto the surface. Now we set the relative position, set, focus on sample, and focus on tip. So now we can focus on tip. We see that the AFM system now knows where the tip is, and we can focus on sample. So this is the sample now. All we need to do now is start tip approach. What the system will do is go down to the position that it thinks the sample is, as close as possible. Move to pre-engage. This is the one. So at this point we should be quite close from the surface if we haven't crashed. And we see that at the moment the tip is, the laser spot is on top of the cantilever. It should be at the end of the cantilever. And we also see that we can see the surface and we can see the cantilever. Next step is to calibrate the spring constant and the Q factor of the cantilever, and also the resonant frequency. So we go to the thermal panel and do capture thermal. Let me see what the thermal is doing. So this is the whole frequency sweep here of in the Asylum system. What we see is pink noise on one side, and what we see is another clear peak at approximately 70 kilohertz. This is the typical 70 to 80 in this case. This is a typical peak for this type of cantilever. I'm going to expand. So I'm taking data at best resolution to make sure that I have very high accuracy for the peak of the resonance, and I'm getting about 45 samples. That might be enough. So now I stop. What I do next, I should know more or less what the conversion from nanometer into volt or volt into nanometer is for this type of cantilever. At the moment I'll put 453 because I know that that should be more or less the value for this particular system. And the next thing I'll do is initial feed thermal. So we see that we have 53 nanometer per volt because I inputted this value. It's predicting a spring constant of 2.85 nanonewton per nanometer, a Q value of 177, and the frequency is 77.853 kilohertz. So at this point we're ready to take this frequency, control copy here, go to the main panel and paste it into the drive frequency. What we see is one of the panels of the cipher system tells us the sum, that's the signal that we get from the laser. The deflection should be 0, so I'm zeroing it. We can click as many times as we want. Next thing is to look at the amplitude and phase. Phase should be at 90. If it's not, I'll show you now how to set it at 90, because we are at resonance, we should be at 90. So that's amplitude millivolts. I want to use about 10 nanometers or less for approaching, because I assume that the tip is sharp. I want to use very small amplitudes, so 0.1 volts times 53 is about 5 nanometers of free amplitude. That should be enough, small enough. What I'll do now is check a set point of about 80 millivolts. That's the ratio of 80% relative to the free amplitude. And next thing I'll do is start tip approach. So at this point the system is approaching the surface, as we can see in the signal of the Z voltage. So the tip has finished the approach to the surface, and now we should be very close to the surface. I can minimize this panel, also the thermal panel, and at this point I can again zero the deflection, and I'm ready to engage. So this is 80, let's make it 77, because we see that we've lost some amplitude. The reason why we've lost some amplitude here is because as the cantilever approaches the surface, we might have hydrodynamic damping and other types of viscosity related forces, like the squeezing film force, that might decrease the amplitude as relative to what we had at about a few microns above the surface. What we want to know is the free amplitude very close to the surface, so in this case about 90 millivolts. So what I'll do now is just engage. We see the Z voltage going down and hopefully stopping here. If it doesn't stop, it's okay. What we should do is to stop, decrease the set point, and try again. This was a false engage, so I engage again. My experience tells me that when you get a false engage, it's typically because the tip is not as sharp as you would like. So it's not engaging. What I'll do is I'll try tip approach again with a small set point. So now it should be fine. Let's try to engage. Okay, so now we see that the piezo stopped in here. That implies that we reached the surface in the second attempt. So now we're ready to take an image. Let's say take an image of 500 nanometers at a 2.4 scan rate for 256 pixels, and we can do frame up. This is a graphite sample, and we've been quite unfortunate to find some very strange feature here in the middle. What I'll do is just move to the right. And even a bit more to the right. Okay, so this should be a relatively good image now. So what I'll do now is frame up. So this should be the surface of a calcite sample. What we see here is the height signal, the amplitude signal, the phase signal, and the piezo signal. So we could go on and take the full image, but I'm not going to do that because we just need to take a few force curves in a point. So what I'll do is stop. So in go there, we can see the tip and the markers. Next thing I'll do is I'll show the marker, and I'll pick the marker and put it in a position where I want to take force curves. This position might be okay because it seems that there's nothing around. So I'll just say go there. As we can see, the tip has gone there. I say that's it, and now we are very in a position of our choice to take force data. Next thing I'll do is I'll call dumb or full or anything that you might prefer to make sure that I don't mistake this data for actual data, because this data we'll take now is just for calibration purposes. So what I'll do is engage. I'll do tip engage now for this position. We see that we engage, and all that's left is to tell in the force panel how far from the surface we want to be. Reason being, we want to get again the calibration of the Q factor, resonance and spring constant from the force curves as taken very close from the surface. And I'm saying force curves as well because we'll use the curves to actually calibrate the volt into nanometers conversion. So first thing I'll do is I'll set a trigger point. 20 millivolts will be the smaller one. We want to be about 50 nanometers away from the surface, and I'll just say single force. What we see here is an image of deflection, amplitude and phase. We know that the amplitude was about 70 to 80 nanometers. By pressing Ctrl I could put the marker on top of the amplitude, and it actually tells me the free amplitude, that's the amplitude before the amplitude starts to decay, a few tens of nanometers before, is about 72 millivolts. This should be the free amplitude, calibration of free amplitude. The phase should be 90. We see here there is 93, so we need to tell the system that it's actually not correct. So we need to go to tune, phase, and we need to decrease by 3, approximately 6. Okay, so next thing to do is to take another force curve by pressing single force. So this is a new one. Let's check the amplitude. It shouldn't have changed. The amplitude is 72 millivolts. The phase now is 90.6. Experience still tells me that you should never go below 90 here in this step. If you go below 90, you won't get the actual data. If you have 91, it's fine because the software will actually correct and tell the system that this should be 90 exact. But anyway, it should be good to be approximately at 90-91 degrees here. So next thing I'll do is take the thermal. So I'll go to the thermal panel, and I'll make sure that the system, before it does the thermal, stops at the right location. So I'll take shake relay off, so it'll be off. XY high voltage, it'll be on. Z-volt high voltage on. LVDT drive on. PAS loops on. So basically this by clicking in these 4 spots, what we making sure of is that the cantilever will stop at exactly 50 nanometers away from the sample, from the actual contact region of the sample, and it will perform the thermal capture. So now all that's left is do the capture of thermal. Let's see the panel. Thermal. So this is the new thermal now. We should take approximately 30 to 40 at least, in my experience. So now what I'll do is stop thermal because this is just for exemplifying force acquisition anyway. So I'll stop here and I'll go again and I'll expand. Okay, so this should be the peak now. We remember that we should have a frequency of 77853. What I'll do again is initialize feed and feed thermal. So instead of 5.3 now we have 831. So actually it's a few hertz smaller, and this should be the right one just above the surface. So what I'll do is copy and paste. So this should be the real resonance above the surface, and we're ready again to take a single force. So we'll check the amplitude again. It should be more or less the same. Yes, about 72 millivolts. And the phase now is 86 because we've changed the resonance. The phase has changed, so we need to add 4. 70 here. So let's take it again. Single force. The phase here is now 90. You can see the phase here, but it's best to see it here from this panel. Why 90? It says 90 here because I put the marker here. If I put the marker here, it'll move to 125, so I can make sure I get the right number. So this should be about 90 in this region. So at this point we've calibrated the cantilever, but we don't know the actual involts. So what we can do is go on the amplitude region, more or less approximately the middle of the curve in here, and we'll go to the calibration panel in the force panel, and we'll say calibration, set sensitivity, amplitude in volts. So that tells us 47.82 nanometer per volt, which was actually a bit smaller than what I expected. Do now is go to the thermal panel. Actually, it's done it for us automatically, and we can do initialize fit again and fit thermal. So the constant, the spring constant now has gone to 3.47 because of the new calibration. The resonant frequency should be the same, and the Q factor should have changed. So now what we need to do is note this amplitude in volt, note the spring constant, and note the Q factor. That's all we need for the force reconstruction process. At this point, we're ready to take data. So this takes us to the last step for data acquisition for force reconstruction. First thing I want to clarify is it's very important to get all the points versus force versus distance points. To do that, we will employ a method called the smooth transition method. So what that does is the free amplitude will be very large, and large enough that the tip will never be trapped onto the surface. So we make sure that we can access all the distances on the surface. So what we'll do first is we'll keep increasing the drive amplitude from the main panel. We go to the drive amplitude, we keep increasing. So first I'll go to say 200 millivolts. The force distance is 50, so what the system will do is go down, the amplitude will decrease to 20 millivolts, and then it will go up and stop 50 nanometers away. So I'm ready to go single. Okay, so what we see is that the amplitude still decays, the phase goes up. This is above 90, so the repulsive regime hasn't been reached. So I'll keep going up. This is the first step to find the smooth transition that I'm talking about. So I'll go to 300 now. Say 380 millivolts. I'll do a single force. Okay, so the repulsive regime was reached here. So what I'll do is go down again to make sure that I get the right value for the critical amplitude, and I'll explain in a second what the critical amplitude is. Okay, so the attractive regime is reached here with 320 millivolts because the phase only goes up. If I click and go to say 350 or 60 millivolts of free amplitude, and I do single force, the repulsive regime is reached. So we see that the amplitude goes down, then it goes up, then on approach, when it gets to the bottom, it goes up again, and then at another point in the curve it goes down and back to 50 nanometers away. So what happens with the phase at these positions of jumping, the phase goes from above 90 to below 90 degrees, and this is the position of bias stability, and the minimum values of free amplitude at which this happens we term critical amplitude, which is, as we saw, in between 0.32 volts and 0.36. So we could approximate to 0.35. I know this system quite well, and I know that if the tip radius was 10 nanometers, the critical amplitude would be about 0.15 or 0.20. So because 0.36, the tip radius might be a bit larger than 10 nanometers. So next thing to do now is reach the smooth transition. How can we do that? So one of the tricks, very fast trick to do that, is to take an amplitude, a free amplitude, 3 or 4 times larger than critical amplitude. So to do that, the first thing I will do is I'll allow the cantilever the first time go really far away, because the amplitudes I'll use are very large, say 200 nanometers away. I'll just click and I'll allow the system to go 200 nanometers away. At this point I'm safe to increase the amplitude from 0.36 to say 2 volts, which is about 6 times. So no, let's do 1.5. 1.5 should be enough. So I'm increasing the free amplitude now, and I'm safe. I'm not touching the surface because the cantilever was 200 nanometers away. 1 volt should be 40 something nanometers, so 1.5 is still much less than 200. So say 1.5. This is okay. This should be okay. So at this point we should be very careful and not press single force. If we do that, because the amplitude is so large, when the tip goes to 20 millivolts minima, it will crash, so it will be damaged. So the next step that I will do is put a trigger very close to the free amplitude, say 1490. So this will be the trigger point. So the free amplitude is 1.56 volts, the trigger is 1.49. So this should be a very small decrease. If I just press single force, I see that the amplitude decreased as I thought it would. Actually, we reach already the repulsive regime in the phase image, as we can see here. So what happens is that we don't see any transition, discrete transition anymore, but the phase goes above 90 degrees and then below 90 degrees smoothly. This is the smooth transition, and this is the transition at which forces versus distance curves show us that we can access all the distances and all positions. So the system has got enough kinetic energy, say, that it will not be trapped onto the surface. So next thing I do is I decrease the force distance to 20, because this is the only region I'm interested in. And as we can see, this is only 5 nanometers of interest, so I'll go about 20 nanometers away, and I'll just press single force. So as we can see, the amplitude now is going down and up through the same path. Also the phase is going through the same path, and we get the phase transition from above 90 to below 90 continuously. So there's no abrupt jump or discontinuity, and this is actually the smooth transition we were talking about. So all that's left is to give a name to these force curves. Let's call it graphite, force curve for graphite, and I'll just say continuous, and I'll take a few curves here. So as I press continuous, data is being taken at a rate of 0.91 Hertz. The velocity is 36. So if we want to take faster scans, what will happen is we will not have enough points to reconstruct the force. So I'll leave it at 0.91, about 36 nanometers per second seems to be good enough for the data here, which is the data of interest for reconstructing the force. So we got already 27 data points. For purposes of showing how to get data, this should be enough. So that's it. Now I can do stop force, and I can actually go stop. So now the cantilever went up to a safe position, and all that's left is to look at the master force panel and look at the data we just took. So this is the master force panel here, and if we go to the data that we took now, we can see here the data. This is the phase, this is the amplitude, this is the deflection. We could actually see the values by clicking on edit. So what the cipher does is it gets 1, 2, 3, 4, 5, 6, 7, 8 columns. The first one is cantilever position, second one is deflection, cantilever position on retraction, deflection on retraction, amplitude on approach, amplitude on retraction, phase on approach, phase on retraction. And that's all the values as in a vector form. This is why it makes it very good to work with MATLAB. Problem being, MATLAB doesn't like this type of data here. So if we want to collect this data and throw it into MATLAB, we should put something here, say zeros enough, or we can just delete that and convert it into a matrix, full matrix. So all columns should have the same number of elements. Another thing that we do here, and this is a software that we provide with a Mendeley Force project, is we can go directly into the data acquisition from Asylum where it's being saved. So you can choose where to put your data here, browse. At this point it went to project video, so it's being saved in 16th of May 2016, and the project video, so it's on the Asylum research data. That's what I'll do. I'll go on the Asylum, my documents, Asylum research data, and I'll do, I need to find the point. It was 16 here, project video. So here's where the data should be, and there it is. So all that's left now is to check this data, and I can just copy paste it into a disk or a USB and take it to the MATLAB box. So I just take this data in the IBW format, and I just copy it into a folder for MATLAB processing. And that's the end of the example that shows you how to take data with the Asylum Research AFM to convert it into force distance profiles and then to process with the Mendeley Force project.